It's all showing. Great. Well, thanks everyone for who dared to come back for this second talk. Yeah, as Bruno said, I put my slides for this talk on the webpage and the drafts of the lecture notes, which is quite choppy for this one. And I'm going to change a few things just so that these lectures more closely follow some of the things that have been going on in the conference as well. So it'll be that way it all ties together nicely. So today I'm going to introduce for you a Siegel model for infinity modular operads. That's the main point, but there's a lot of other things happening in this talk. So it's a bit faster than the one yesterday. I just want to recall a couple of facts. So yesterday, what did we talk about, right? So the main thing was that we had this notion of C-colored modular operads. So given a modular operad, I can take this functor that we called the nerve, and I can land in a category of graphical sets or set valued presheaves over U, which satisfy a strict Siegel condition. So remember, U was our category of connected graphs. So today we're going to specialize down. As I said yesterday, I started with a very abstract definition of modular operad. And today we're going to move on to one-colored operads for the rest of the talk so that things are a little bit simpler. And so I'm just going to remind you of a definition. It's going to look a little bit less abstract than what we saw yesterday. All right, so a modular operad for us, I'm not going to sort of emphasize that it's one color. This is going to be a collection of objects, so P with indexed by N, where each Pn has sigma n action, symmetric group action, so a symmetric sequence. And then I want a family of equivariant associative composition maps, which I'm going to write with the circ ij. Right, so here, this means that I'm thinking about this element. This is an element of P4. This is a little leg that I've labeled I. This is an element of P3. This is a little leg that I've labeled J. And I've decided I want to compose them. So I glue them together. And then I can contract this internal edge it down into something that lives in Pn plus n minus 2. Oh, sorry. M and M have values. P4 plus 3 minus 2, which is 1, 2, 3, 4, 5. Okay. So this is just to remind you of what we're thinking about. And so I can connect any I and J's, right? So the main thing is that I have these little spiders as my operations, and I can glue them together. And I also have so that's a cyclic operad. And then if I want to add a sort of abstract trace or contraction operation, I noticed that the last picture was for some reason going the opposite. But yeah, I'm drawing these rather quickly, so sorry about that. So a family of equivariant contraction operations. So here I'm taking a little spider that lives in 2, 3, 4, 5, P5, and I'm allowing myself to contract an I and a J. And I'm going to say that this here now lives in P3. Okay, so it's sort of an abstraction of the trace. Just a refresher of the definition without thinking about colors, making it a little bit simpler. Okay, oops, I realized I've covered the chat here. All right, so what was our theorem yesterday? So our theorem was telling me that if I take a modular operad, so one colored modular operad, I can construct this little object NP, this graphical set, and I have the evaluation of that functor at a star is going to be my set n, like living my nth entry in the symmetric sequence. I guess that's the precise way to say it. And that I have these bijections, or now I've upgraded to an isomorphism, but I have a bijection here from the evaluation NPG to the product over the vertices of the evaluation at the stars, right? So this is the Siegel map. And just to put this together with the picture I just drew, what I'm saying is the modular operad compositions and contractions are modeled by, so here I have this bijection, and I'm thinking of that product where I had these little spiders here into my graph, and then I can always contract down to the corolla of the graph. I didn't mention this graph yesterday, but it's this map is always there. That's part of the graphical set structure. So I thought I would mention it today. I got an email, someone was asking me how this exactly looks like a modular operad. So now I feel like I've answered that question. So if you're still curious about that, please let me know again. Right? So there's this little piece that was new to your life today. Okay, so so we know how to go from modular operads to set valued pre-sheaves. All right, so our goal today is to think about what happens when we have pre-sheaves where our Siegel maps are just homotopy equivalences. Right? So where this map from, so here X is going to be living in, I'm going to upgrade so that I have a place where homotopy equivalence makes sense to space valued pre-sheaves. And I want the Siegel maps to be weak homotopy equivalences. So this will look like a modular operad, but a weak one. So the goal for today, and as you can see, is kind of a long list of stuff. So it's going to be a bit chaotic to get so that we are prepared for the third talk. So I'm going to talk about space valued pre-sheaves. So graphical spaces maybe is what we'll, to align more with the dendroidal language, I'll try to say graphical spaces. We're going to describe the weak Siegel maps, so just how you weaken them. And then I'll explain the motivation for these, which is this profinite completion of modular operads, which is something that we need for tomorrow. And then I promised you that I could tell you about all the different ways your favorite definition of a modular or cyclic operad, how you could derive it from U, right? Because this is kind of an abstract version that most of us probably don't actually work with when we're thinking about modular operads. So I want to show you how you can specialize down. And then I have a couple of nice open problems at the end. Okay, great, let's get started. So what is category of graphical spaces? So I'm just going to take this to be space valued pre-sheaves. So remember what I mean by a pre-sheaf is a functor from A up and now to simplicial sets. So you've probably already noticed, but I massively abuse language and I always just call simplicial sets spaces. And throughout, there will be model structures later. I'm going to be thinking always of the conquilin, like the classical model structure on simplicial sets. So we're going to use the same notation as yesterday, and I'm going to write like X sub G for the evaluation of this functor at G. And I'm going to use the same definition of the representable. Okay, so evaluation of U at G. This is still a set value pre-sheaf, but I can think of it as living in spaces via an inclusion. Right? So sets, they're just sitting inside simplicial sets. And remember again, this is the set of maps, so the evaluation of the representable at any graph H is the set of maps from H into G for all H in U. Okay. Slow down a sec. Okay, sorry. So I also wanted to say that there's not that many easy exercises for today's lecture. So I have one easy exercise. If you get lost after this point, this is worth doing if you've never done it before. So most people who have seen this will be familiar with this type of thing. But if you've never seen it before, you can play with this. So my exercise is to show that the evaluation of a presheaf at G is in bijection with, it's probably better to say than equals, the maps from the representable, the set of maps from the representable at G into X, right? And this is, you know, if you've really never seen this before, this is the Yoneda lemma, which I just misspelled. I'm not going to write that. My spelling is terrible. I'm a product of Texas public schools, guys, which is that's why I don't like to have anything handwritten. All right, so this is just if you get lost after this point, and I'm going to use this fact kind of freely, and so it's worth playing around. All right, excellent. So I want to introduce this notion of Siegel core, and in order to, you know, the Siegel map that we talked about yesterday, I talked about these corolla ribbons, and I'm going to want to relax those corolla ribbons so that they're homotopy limits and not limits. And so I need to introduce a new structure. And every time I've explained the Siegel core to my students, we tend to get hung up on this. So this is a different way I'm going to try. And we'll see how this works. So remember that like any graph, I said, you could think about a graph G. This was a diagram, right? Aside from the fact that all the weird stuff we did with graphs, this is a diagram in the category of finite sets in the shape of I, where I was this thing that was this category in this shape, where this is a monomorphism and this is an involution, right? So it's a diagram category. So I could actually view, sorry, there's a non-trivial chance my cat is about to interrupt this talk. I can actually view G as a connected graph, G as a co-equalizer in this set. So let me explain. So if I take any connected graph with non-empty vertices, we can write out G in this way. And so how do I do this? I'm going to choose an orientation. So let me show you. So first, I'm going to choose an orientation. On the internal edges. So basically, I'm just going to take, so here's E1, E2, and E3 in my example. And I'm going to draw some arrows. Okay. Basically, what I'm doing is, if you think about how I have these little labels, like this one is A and this is a dual, I'm just choosing which one I want to be the dual. That's what I mean by choose an orientation, just so I have some control over what I'm doing. And you can always do this. Now I can look at I can define two maps. So I'm going to call this F and I'm going to call this G, mapping an internal edge to the star of vertex. So I'll have F take inputs, maybe call it inputs, and G will be outputs. So these arrows that I'm drawing here are actually meant to be like defining input and output. So if I draw now my diagram, okay, so here I'm going to write E1, E2, and E3. And I'll write B and W. So I have the map from, so E1, right, we know as we, oops, sorry about that. As we saw yesterday, is attached to B. And it's attached to W. So using this thing, I'll say E1 is attached to V by G, and it's attached to W by F. I have E2 touching V, and this is an input, so this will be an F. And E2 going to W, this will be an output, so this is G. And E3, well, I have both an F and a G here. And the thing is, if you check in this, if you take this co-equalizer in the category here, this diagram category, G is what comes out. Okay. So no, this is not in U because these are not objects in U. So because these are not connected. So this is not something that's happening in U. This is just saying that I can write G as a co-equalizer based on its internal edges. And so what this is saying is that the internal, right, G is made up of its vertices plus the data of how we glued it together.
If you mean, there is a question here.
A small
Yeah.
question. So when you say this is equal to the co-equalizer, so you forget about the leaves, right? They are not included in the data.
Oh no, yeah, they're not there.
So
Well, I mean, I'm mapping, I'm mapping, the leaves are in the vertex. So this is the star.
Yeah.
Right.
Okay.
So this is these, so they're there, but the only stuff that is getting identified are the internal edges.
Okay, that's good. Thank you.
Yeah. Thank you. Okay. So the Siegel core is a version of this identification, but happening at the pre-sheaf level. So I want, so this example of thinking about a graph like this is what the Siegel core is supposed to be doing, but in the pre-sheaf level.
You have a question, Marcy?
Oh yeah. Probably, yes. Yeah, sure. Yeah, yes. Sorry, the question to read out loud to everyone is, this looks like a co-end construction, is it right? I haven't, yeah. Without actually checking that at all, yes, it's a co-limit, so. Okay. I'm not trying to do anything fancy. Yeah?
Can I ask you a question?
Of course.
If you compare this construction with the one you have also, I think, explained in an earlier paper with Phil, where you use directed graphs, so for props.
Yes.
Then it's very similar as a construction, but I have the impression that here you have a choice.
Yes.
When you work with directed graphs, you have no choice. Is this difference important, or is it not so important for?
It is not so important for this, but you're right that in the directed graphs you have zero choice. This is strict what's going here. So it is true that we've artificially done something. All right, I chose an orientation. The thing is, if you choose a different orientation, you'll also get the same graph. So it doesn't actually change things, but it is you are correct that it's a bit weird. So you have to check this, and it's true, but it's weird that it doesn't matter which choice you make on this orientation. So you could write this out entirely in terms of the half edges and involution, and then it's like a little bit more clear that it's well defined.
Okay,
but you're right, that's quite subtle. Yeah. Right. So the Siegel core is, I want to take this idea of the graph is obtained by gluing together the edges. Right. The Siegel core is precisely that, except for now I'm taking that data in, I'm taking that co-equalizer as a pre-sheaf, as a set value pre-sheaf here. So what is the Siegel core, right? So I'm going to have that diagram that I guess I can copy it. And of course that I'm not very clever with this thingy, but allegedly it works. All right, and you just apply U here to all of these things. This is now like the star of B, and reverse the arrows, of course, and so on. So I'm going to make this really ugly. I guess we always have time. And so on, right? And this is what the Siegel core is doing. And so I'm going to erase this hideous diagram because it's distracting. But you get the point. So this is an object. Well, where does it sit? It's inside of the representable pre-sheaf. So the embeddings that take the star vertex into G, these induce maps from the Siegel core into the representable. Right, and we're going to give these guys a name. These are Siegel core inclusions. And because I have one special graph, this exceptional edge that has no vertices and so doesn't have a nice description this way, we're going to just define the Siegel core of this guy to be equal to its representable. So this is just the identity map in that case. Okay. So to bring it back to what we said yesterday, so the Siegel core is basically the co-limit that allows you to, when you map out of it into X, you get the limit that I talked about yesterday. Okay? So this is the object from yesterday, the corollary event from yesterday. Right, but this doesn't depend on X at all. So this depends on the graph G. So the Siegel core is a thing, and when you maps out of the Siegel core will give me that corolla ribbon that we discussed yesterday. So I'm going to leave as an exercise. Just checking my timing. I'll even label you some edges. And you can pick your own, and you can check that this is true. So luckily when in the category of sets, right, you can just take the limits and check that this is true, and it can be very illuminating I recommend it. So I give you graphics, I give you homework. Right. So, right, if we take our Siegel map from yesterday, right, so reminding ourselves what we have, where we have, I'm going to stick with one colored things today. So X evaluated at the exceptional edge will be a point. And from our first exercise, we know this is the set of maps from the representable into X. And now the Siegel core into X, so if this is just a 1-point thing, then we know that this identified with the product here, right? So this was using the facts from the previous lecture. When this is the point. So in this case, right, in our one colored case, the Siegel map now looks like, all right, I have a map from X evaluated G, which we've identified as the set of maps from the representable into X, into the product of the vertices, which we've identified as the map from the Siegel core into X. So our goal for weakening this is to replace this, right? We want to make this all up to homotopy. And so the way we're going to do it is we're going to replace these with derived mapping spaces with some up to homotopy maps, right? Let's make everything up to homotopy. Yeah, so Joachim added in the chat, and it's fair enough. It is not strictly necessary to make the choices that I made for orientation. So there's a canonical diagram. This is a co-limit over, and is essentially the edgewise subdivision of the graph. And I'll leave the rest of it. So yeah, it's easier to explain this way. So yes. But thank you, Joachim, for answering that question. So we're going to replace this these maps here. All right. So here's my first definition of what a Siegel modular operad should be. So I'm going to take, I want to go a little bit fancier than sets so that I actually have a weak homotopy equivalence. So I'm going to go into spaces. And I'm going to say that a pre-sheaf or a graphical space is Siegel if first I have this equal a point. And second, that the Siegel map, and now I've written this with derived mapping spaces, is a weak equivalence in simplicial sets of spaces for all G and U. Okay, so some notes on what I'm saying here. So one, the thing I've highlighted, this is strictly speaking not net needed. I'm going to assume it throughout because it is needed for one theorem at the end of this talk. But you can get rid of it if that makes you happy. So what I've written here as the derived mapping space, so I mean that this is well defined in any category that has weak equivalences. So it's a fact, I guess, that so UAP has several model structures. And you can pick whichever one you like. And so there's a natural one, that's the projective. And this has weak equivalences. So this is a model structure that exists on any diagram category. And weak equivalences are defined entry-wise. So I'll say that X is weakly equivalent to Y if the evaluation at every G is a weak equivalence of spaces. Okay. So I have some well-defined notion of weak equivalence, and then map H here, well, right, this is what I mean by, I'm just writing A to B, so modulo, so where I've inverted up to weak equivalence. So the homotopy classes of maps, if you're not familiar with that notation. So this is a perfectly fine definition of what would be a Siegel modular operad. So, and you could use whatever model structure you want. I generally try to avoid working with mapping spaces. So if you don't know anything about Siegel cores or X's or cofibrancy and fibrancy, these are very hard to work with. Right, I tend to get anxious about just plain mapping spaces. So what we're going to do is put a Reedy model structure on this category of presheaves on graphical spaces. And in that case, I'll be able to say that the Siegel core is cofibrant, and then I can put a condition on X where it's fibrant, and I can get rid of the derived part of the mapping space. I can identify it with the regular mapping space. So we'll get, let's do that now. So I have this definition here. I don't expect you to absorb this full definition on the slide. It's here for consistency or sort of completion, I guess. So a generalized Reedy category. So this is a this is in a paper of Berger and Moerdijk. So a dualizable generalized Reedy category. So this is a small category R. Oops, sorry, a small category R, which has a degree function. So something that assigns a notion of degree to objects. And then we define two subcategories, one that raises the degree and wide subcategories, the one that lowers the degree. And the main thing to take from that is then that every morphism in the category factors in such a way that first lowers the degree and then raises the degree. So we just want to have a case that we can factor all of our morphisms in some defined way. Right? So it's a factorization on this. And the reason you like a nice Reedy structure on a category. So I know I'm going fast, but I wanted to add the definition and also not talk about it at the same time. So please let me know if you need me to slow down at any time. The reason we want to know about Reedy structures is that there's the theorem of Berger and Moerdijk is that if you have, when you have a dualizable Reedy category, generalized Reedy category, and some nice ground model category, I didn't want to list a bunch of things, but all of our examples today will be nice enough, then the diagrams, the presheaf category admits a cofibrantly generated model structure with level-wise weak equivalences and Reedy fibrations and cofibrations. So basically this will be, yeah, so this is a nice diagram category where we sort of have, like Reedy fibrant diagrams have nice properties. Homotopy limits tend to be equal to limits. So that's one of them. All right. So we have the Reedy structure on U. This is one of the reasons that we define our morphisms the way we do. And the degree of a graph is going to be given by taking the number of vertices. So I'm going to say the degree of G is the number of vertices plus the number of internal edges. This little I sub E is internal edges, if I didn't define it before. And so this, our graphical category is generalized Reedy, where the minus graphs are, sorry, the minus morphisms are the codegeneracy maps. Right, and so let's remember what those look like. So locally, I have a vertex and it disappears into an edge. So that's lowering the degree. Okay. And then my plus category, so this is going to be generated by those elementary inner and outer coface maps. Okay, so remember that the inner coface maps, well, they are the things that explode a vertex and add an internal edge. So that's going to raise the degree. And the outer coface maps are these embeddings, which don't lower the number of vertices, but they do increase the number of internal edges. So they are going to raise the degree. And so a direct result then of the theorem of Berger and Moerdijk is that we have a nice model structure on this category of graphical spaces, where we have level-wise weak equivalences still, but we have a sort of a nicer class of cofibrant objects. In particular, the Siegel cores are cofibrant. So in fact, that's my exercise. So if you're not familiar with model structures, this is maybe not a great, this is kind of a hard one if you are. But so Siegel cores are cofibrant in this model structure. And this is not too hard to figure out if you can compute latching and mapping spaces. So it's actually kind of fun. Well, maybe my definition of fun is different than yours, but this is actually a reasonably fun thing to do. And it's quite easy to see examples of graphs in which the Siegel core fails to be cofibrant in the projective model structure. So you don't have to work so hard to come up with an example where this is not cofibrant in the projective model structure. And this can be useful for figuring out what's going on here exactly. That's my exercise for you. Okay, if anyone needs a hint, you can ask me. Great, so now I can give you what I would call the real definition. So a definition for Siegel modular operads. So I'll say that a graphical space is Siegel if the evaluation at a point, the evaluation at the exceptional edge is a point. If the whole presheaf is really fibrant, so it's fibrant in this model structure, and the Siegel map here is a weak equivalence of simplicial sets for every G. And so here I'm using the Reedy structure, and when I write my Siegel map in our recognizable definition. So here I can pull this, if this is fibrant, this is fibrant, this is cofibrant, I can get rid of this little h, and in fact the sort of homotopy limit, it identifies with the limit in this case. So I really can write my map the way that I was writing it for sets. It makes my life a little bit easier to understand what a Siegel guy is. That's the reason for those structures. Great. Great. So we actually have a huge class from the nerve theorem that we talked about yesterday, and we have a huge class of Siegel modular operads. These are just the nerves of already known modular operads. So if you start with a one-colored modular operad and you take its nerve, if it's one color, it's going to have the evaluation at the exceptional edge a point. And the Siegel map is going to be an isomorphism, so it's in particular weak equivalence. So I'm going to say that every one colored modular operad gives you a Siegel one. And I'm going to put, though, sort of up to possible fibrant replacement. I didn't say anything about So you might have to be a little bit careful about some vibrancy conditions, but you can always sort of transfer your favorite modular operad over. And we have a classification of these objects as the vibrant objects in a model structure. So basically, the category of graphical spaces admits a co-privately generated model structure. These vibrant objects are the Siegel modular operads. And I won't say much about this because this is just a left Bausfield localization of the model structure. And you sort of localize along the Siegel core inclusions. And again, I'm happy to tell you more about this, but I am guessing that my version of fun might be slightly different than the audience's. So this will be the most thing I say about it. Great. So in other words, I have a good model for infinity modular operads with one color. So just some remarks. So just a few things that I said. So technically, I talked about spaces, but this actually works fine in nice Cartesian monoidal categories. So you can look at presheaves in here in groupoids or categories. So this is groupoids and small categories. All right, so we've been talking a lot about groupoid operads and groupoids in this workshop, and so same thing we're going to talk about modular operads and groupoids in just a moment. And everything that I said works fine in the same exact way. Right. So that's good to know. And also, you don't strictly need this requirement that you're in one color. So what we have written down is that we require that this to be a contractible space of colors. And again, that also is probably not strictly known, just the left Bausfield, not needed. The left Bausfield localization gets real tricky if you do multiple colors. And at the time of writing the paper, I couldn't think of an example of of a colored opera that I would want to be weak. That would be worth it for me to do that localization. So that's the reason that exists in that form in the literature. Okay, so now you all know everything about infinity modular operads. Where did this come from? So we're going to talk about profinite completions. So you saw in Damian's lectures already the notion of pro-unipotent completion of operads, right? So that he mentioned, you have this operad of parenthesized braids, and it's not so interesting on its own, but after you do this rational completion and take the automorphisms, well, we get the pro-unipotent version of GT. Okay? And so there's another interesting completion, which is the profinite completion of groupoids, of in fact this operad, and jump right in. And that's where the necessity of infinity is coming from. So for a discrete group G, right, the profinite completion is just the limit over all of its finite index quotients by normal subgroups. So I probably could have come up with a more original example, but first example that comes to mind, right, the profinite completion of the integers is the limit over all these quotients by Z mod n, where your maps go from Z quotient Z mod n, I don't know what to call that thing, Z mod m, whenever m divides n. So, yeah. Maybe actually a more interesting one to think about is the profinite completion of the free group. this will be coming up tomorrow. So that's a more interesting one to think about a bit. Right. And in fact, if you have a nice enough groupoid, you can define this. You can also define the profinite completion of the groupoid G. And nice enough. So I think Geoffroy is the real expert on this, but I'll say that if sort of G has finite objects, that's certainly nice enough, and maybe that can be relaxed more. I'm not sure, but we'll say that's good enough. Okay. So you have this notion of profinite completion of groupoids, and then the question happens. So we saw how did this work for pro-unipotent completion in Damian's talk, right? So we had, when we write this PAB hat, well, that means we're going to sort of complete each groupoid at each n. Oh, now there's like Q's everywhere, right? And that this pro-unipotent completion was a symmetric monoidal functor, and so the completion of the parenthesized braid operad was still an operad, because we can always sort of pull the operad structure across symmetric monoidal functors. So if you take an operad in groupoids, a modular operad in groupoids, and this is true for operads as well, that's why this is in parentheses, and you could also throw cyclic there, is the profinite completion of the operad still a modular or cyclic, etc. operad in profinite groupoids? Okay. And we have a theorem of Geoffroy's that says the answer is yes. So if you have nice enough groupoids, so if C and D are two groupoids with finite sets of objects, then this map from the completion of the product to the product of the completions, so this is given by the two projections, right? That's where the map comes from. And this is an isomorphism. So that means that you can, in fact, I guess lax monoidal functor, but you can profinitely complete your operad and get still now a modular operad in profinite groupoids. Giving time for, and that you get some great things from this, just like with what we've seen in earlier lectures, right? So Geoffroy has a theorem that says, so there's an isomorphism, I'm just going to say automorphisms, there's a little sub-zero, this means which fixed objects. And that's isomorphic to the profinite version of GT. So when you look up of the parenthesized braid operad, so like what you've seen already, right? The parenthesized braids are not very interesting somehow, but when you complete them, you get this big interesting group. And the profinite GT, we'll be talking about this much more tomorrow, but this is quite somehow very cool. It contains the absolute Galois group of Q. It's a big and interesting group. And so this we'll definitely talk about more tomorrow, but similarly, there's a different operad in groupoids of parenthesized ribbon braids. So just braids with a little twist on them. And a paper with Pedro Bolera and Geoffroy and myself says that, in fact, you can, when you look at automorphisms which fix objects and you profinitely complete, you get profinite GT. So there's some missing hats everywhere. All right, so this is using the fact that this profinite completion is it behaves well with products for groupoids. But we actually kind of want to look at what happens in spaces, like when we take the classifying space of this. So Geoffroy mentioned yesterday, and I think there was some more that, oh, sorry, I had one more thing I was going to point out. Right, so again, so thinking about the nerve theorem and placing this into context, right, we have the nerve of this is actually an isomorphism. The nerve of a profinite complete G in groupoids, this should be profinite groupoids, is going to be an isomorphism. So we still have the Siegel map here because we have an operad. So modular operad, implies Siegel map is an iso. Still hanging around here. So, okay, good. What we're actually kind of interested in is how, it's what happens when you look at these, the classifying spaces of these groupoids. Okay, so I'm gonna have the functor B, this is gonna be the classifying space functor. Of sort of a groupoid. And this is symmetric monoidal. So if you apply it to a modular operad in groupoids, I'm going to get a modular operad in, oh, sorry, this is supposed to just say spaces right now, the typo. You're going to get a modular operad in spaces. All right, and so now the question is what happens under profinite completion. So, oh, maybe I want to say a little bit about what we wanted to say there. So, right, so it was mentioned a couple of times during the lectures that, right, parenthesized grades, if you take the classifying space of this, right, I guess I'm going to put add an n, that this is equivalent to the little discs, the space of little discs, right, for the little 2 discs operad. So if I look at the classifying space of PAB, the whole operad, this is the little 2 discs operad. And the same thing, so we might want to know, for example, the relationship about how, if we know that automorphisms, I'll skip. And let's say the one that that we talked about, other ones, PARBN, this is homotopic to the framed little 2 discs on N. Okay. And so this operad, the framed discs, the framed little 2 discs, is very closely related to the operad that we've been hearing about sort of in the background of the Lee-Mumford compactification made up of the compactified moduli spaces of genus 0 curves with n-marked points. So tomorrow I'll be talking about trying to motivate the history of this, but you know, we want to understand how does the profinite Grothendieck-Teichmüller group act on these moduli spaces. Okay. That's sort of a fundamental question because we want to understand how the Afstib-Gawa group, which sits inside of the profinite Grothendieck-Teichmüller group, acts on the moduli spaces. And so understanding what the classifying space functor does for our profinite groupoids will help us understand this action. Right, so again, I'm not explaining it very well right now, and I can like feel it, you know. But this is the topic for tomorrow. But I just wanted to point out that I'm not just doing this because I can, and I really want to have an infinity modular opera. Okay. So together, so we have this proposition with Pedro and Geoffroy that says that if I have two really nice spaces, so X and Y are connected spaces with good homotopy groups. So I'm not going to give this definition, but this is an actual definition. I guess I can if you really want me to, but so these are really nice topological spaces or simplicial sets. In this case, then the map of profinite completion of X times Y is weakly equivalent to the profinite completion of X times the profinite completion of Y. Okay. It's almost never true in general. Right, so in general, profinite completion of spaces does not behave well. Is not, so we just don't have this. We don't have any relationship really. Well, there's a relationship, there's a map, but I'll just put not good. So not a good map, all right? But if our classifying space of our groupoids are these nice spaces, meaning they satisfy the conditions of this proposition, then the Siegel maps for the nerve of this completion, these are weak homotopy equivalences, and this gives me a Siegel modular operad. Right, so if everything works out nice and my groupoids are nice so that my classifying spaces are nice, then I get a Siegel modular operad. This is a, yep. What is a profinite space? So that is a, well, you can define it a couple of ways. So it's a limit over, so, sorry, I'm finding some space here. I'll say it's a completely disconnected Hausdorff space, or you could call it a stone space. Clemens might be more familiar with you if you're familiar with category theory, but it's defined to be a limit. So, and then I'll have some finite quotient, and now I forgot what I'm quotienting over for a second. All finite subspaces. Yeah, so does anyone remember the numbers? It's completely discontinuous cofinite spaces.
No, but a stone space is often called a profinite set.
Oh,
so,
right. Sorry.
A profinite space is a simplicial stone space.
Yeah. Sorry. Yeah, I misunderstood. Yes. So, yes, you have like a profinite set, and then you have the profinite set. So, yes. So profinite space. I misunderstood your question. So, simplicial profinite set. And I actually wanted to,
Can I ask a question? But it's perhaps a nasty question. But
that's all right. I might not answer it then, but go ahead.
You see, I think that I have the feeling that your proposition needs probably, so your proposition probably somehow is very much related to what it means to be a weak equivalence of profinite spaces. weak equivalence of profinite simplicial sets. And you said that it is almost never true. So I would somehow naively suggest perhaps it is true with the right, it is almost always true with the right notion of weak equivalence. I think that you use here a very naive notion of weak equivalence.
Yeah, so we use the notion of weak equivalence due to Girion-Quick. I guess I should have mentioned that, the model structure there. But it's true that there is probably a different way to write a model. I mean, I don't know which model structure on profinite spaces there. So this is the quick model structure on profinite spaces. But that's certainly a possibility of a different way to deal with this this problem.
Thanks.
Yeah, no problem. And I wanted to, right, so again, so going back to where this comes from, and is that, so our motivation for this is that in the case of where we look at the classifying spaces of parenthesized ribbon braid opera, these little groupoids, these are nice spaces. And in fact, we do get then, we can use this isomorphism between automorphisms of PARB, profinitely completed, and which fix objects, and the profinite Grothendieck-Teichmüller group, to sort of understand a GT action on here. And I should say this little arrow is doing some pretty heavy lifting. So that's like not like a direct, that's not a direct thing. It's just, it goes in one direction. I also wanted to point out that, so about 2 weeks ago, there was a talk by Ika Moerdijk on his, I must have spelled Ika's name, gave a talk on, at this exact program. So I guess it's in the seminar, it was for Carlos' birthday, on sort of what is a profinite operad. And that's some joint work with Bloom. And it looks pretty, it's on the, I checked just before this talk, and it's on the website. It's kind of an interesting question that I wouldn't know how to answer. So it's a nice program going on there. Recommend that for more on this. It is a very challenging question. We just know in some very special cases that we can in fact get an infinity operad or modular operad in this case. Okay, and this we do have a reason for wanting to do it. That was sort of my point. All right, so with that point made, and I will be telling you about this stuff tomorrow, so you'll hopefully be even more convinced that it's worthwhile to think about these profinite completions. So with that, I'll sort of take a bit of a hard turn, and I promised I would tell you about all of your favorite variations on infinity modular operads. So to make this a full survey talk. So if you have, a lot of us read about modular operads, so certainly the one that I'm familiar with is from Getzler and Kapronoff, which is defined as sort of genus graded, the moduli space. So MGN, right, the collection of MGN, which we'll just call that, is sort of the canonical notion of a modular operad. And I didn't say anything about genus or grading throughout this whole discussion. So you can define a genus function. That's an L, which looks a little funny. L. Just by putting some numbers on the vertices, you could just assign a genus to the vertex of your graph. So in this picture I've drawn below, I have each vertex has a genus. So this one's genus 4, genus 1, genus 2. Then you can actually define the genus of the whole graph. to be, you first take by taking the first Betty number of the graph G, and then the sum over all the genuses at each vertex, right? So for this graph, right, I have 2, I have a genus 2 object, and then +4, +1, +2 is my genus.
I have a question on the chat.
Oh, sorry.
Is there any other isomorphism to GT?
Are there any so I guess there's the parenthesized braids, frame discs. The answer is probably. So, but they're all going to be like, I think they're all operads, which are like equivalents in some sense. So we have, so PAB. Oh, no, I mean, it's, so I would say that probably for the profinite version, Jaffa's is sorry, if you're not seeing the chat, the question was if just ours was the first computation of automorphisms of a profinite operad that were equivalent to the profinite Grothendieck-Teichmüller group. And I would say that Jaffa's paper on PAB is the first one, and Jaffa's in the audience, so he can correct me if that's wrong, but I'm pretty sure that's the first. And then doing this for frame disks and getting something out of the moduli space, which we'll talk about tomorrow, is, I think, the next. And I don't know, I don't think there are any more at the moment, except for things that are equivalent to PARB in some strict sense, which is also in our paper. So I think that's completely correct. All right, right, and so we can also define a stability condition on our graphs as well. Now, these are some weird transitions today. It's just one of the middle lecture had to cover lots of stuff, so I apologize for that. All right, so a graph will be stable if every vertex satisfies the stability condition. Just going to move this down here. And so in particular, note that any sort of one vertex like this, which is genus 0, this is not stable. Okay, this graph is definitely stable. And you can just change the graphical category that we described before to have objects stable graphs. And morphisms are just going to be graphical maps that are compatible with genus gradings in the sense that they make this diagram commute. So remember, this is the phi sub 1 is whatever's happening on the when I explode a vertex, so that that's done in a way that is compatible with genus. And because this is in fact easy to see its generalized reading, it comes directly from the graphical category U, because there are no degeneracies here. So the fact that this is not stable, so not stable, implies no degeneracies. So this is quite an easy factorization. It's just all inner and outer coface maps and some isomorphisms. So it's very easy category to work with. And so you can define genus graded Siegel modular operads exactly as we did before, with just by replacing the graphical category. So it's smaller, it's easier to work with if that's the thing that you're interested in. Conscious of the time, so I won't go too fast. There is a product here, but it's a bit, I didn't write it because there's this right? It's a limit, but it's also got all these grading things. So the diagram is a little bit nasty, but it works out to something that you could call a product. So it's, it's not a typo. I just didn't want to write something that was too confusing. It's a little bit subtle, but it's not so bad. Right. Great. All right. So anyone who works with modular operads will be thinking about what happens to cyclic case. So this is sitting around inside all the time. And you actually have a nested sequence of subcategories. So which one we'll call U sic, one is U sub 0, and one is called U. And so U sub 0, these are just the simply connected graphs. So these correspond to augmented cyclic operads. So these are going to be things, this might include something that looks like this. And U sic, these are simply connected graphs with non-empty boundary. And these are cyclic operads. So I want to make sure I have at least one leg hanging around to get a cyclic operad. So I don't, this guy is not music. And it's pretty easy to see that these are nice. In fact, they're sieves, so this is a nice exercise for you. You can see that if you have any graphical map and the target, if the target is either simply connected or simply connected with non-empty boundary, then the source must be as well. That's a feature of just how graphical maps are defined. Great. And so there are like several related categories in the literature. So there's a paper by, and I apologize because I don't really know how to pronounce this guy's name. So Wald, I'm guessing it's German, but so Paul, if you're in the audience, I'm really sorry about that. So there's a category that he calls omega sub sic. So this is like a non-symmetric cyclic operad category. And so what's in here, these parameterized non-symmetric cyclic operads, which I think a lot of people like to work with. And note that this is, you can find this inside of the cyclic restriction of the graphical category U. So you just force some cyclic ordering on every graph. And I'm pointing this out so that people can see how to get their favorite objects out of here. So you're going to force some specified cyclic ordering on your objects. And then you look at the subcategory where the maps preserve that ordering. Okay, so I guess if you also wanted somehow non-symmetric modular operads, you could do something similar. There's another category for cyclic operads that we called C. This is with Phil and Donald. And this has just no involution and is a little bit harder to work with, but it has the same objects, just slightly different morphisms. So that's also around. And I don't know if there are other cyclic categories. As we mentioned at the end of last talk, there are actually adjunctions and Quillen adjunctions with the dendroidal category. Omega, so that also sits inside of U, so you can form all of these Quillen adjunctions. It goes this direction, and the composite is also a Quillen functor. And so my open problem, which I think is kind of interesting, is there's like several papers, one by Clark Barwick and one by Hirschhorn and Volek, which they characterize when maps between sort of strict Reedy categories result in Quillen adjunctions between diagram categories. But there's no such thing for generalized Reedy categories. And having such a characterization would A, automatically sort of let me know how to work with all of these different graphical categories, and B, just kind of be a nice result. So if anyone likes to play with generalized 3D categories, I think this is a very nice problem. All right. I guess I sped through at the end here. Great. So now I have to tell you that I've let down everyone in the audience who does algebraic operads. So everything I've said doesn't really work for the for modular operads and chain complexes, right? So you can't work with the Siegel version for algebraic operads because we just don't have these projection maps. Right? This doesn't really make sense. What I just wrote down does not make sense. Please don't write that down. Right? So the idea of the Siegel condition for modular operads and chain complexes is not a good idea. There are a couple of ways that you could choose to model that if you want. And so one is to use this theory, a theory of enriched infinity modular operads. So there's a version for operads by Chu Haugson, and then for properads by Hongyi and Phil and Chu Hackney. And you could extend that for modular operads if you want. I find this a little bit difficult to work with, but it depends on what you want to do with your infinity modular opera. And I think maybe something that's a little bit closer to what people are familiar with. So Ben Ward has, oh, Ben, you're in the audience. Maybe you can jump in on this then. Ben Ward has shown that the operad governing modular operads is Kazul, so for groupoid colored operads. And I think that you could use what he's done to talk about something called strongly homotopy modular operads, which is similar to the strongly homotopy operads of van der Laan. And I expect this model would be equivalent to the quasi-modular operad model that I sort of threw out at the end of the last talk. This would follow from work of, oh, I can't pronounce Bryce's name. Hi, Ben. If Ben wants to say anything about this, I've finished, I guess, 10 minutes early, so I'll stop there and open for questions. Okay. Sorry about that. Yeah.
Thank you very much. Any question here or somewhere else? Oui, vas-y Geoffroy. C'est peut-être mieux, je pense que le micro il vient jusque là-bas. Mais it's better if you come here. I don't know whether the microphone gets the entire room. So.
Oh no, do they have to walk to the front of the room to ask questions, like in school?
Geoffroy is moving from his place to chat with you. No.
Hi Marcy, this is Geoffroy.
Hey Geoffroy, how you doing?
So you mentioned that about Siegel modular operads, about this construction of a model category of Siegel modular operads. I was wondering if you had strictification results
for strictifications. No, so I actually don't really expect that will work. So you mean like where you have like some simplicial modular? Yeah, I would not expect that that you'll have equivalence there actually. So in the non-simply connected case, so and then I'll put here like Siegel modular operads. There's kind of a, well, not kind of, there's an obstruction to there being equivalence here. And it has to do with, well, it has to do with the operad governing modular operads like not being very nice, not sigma cofibrant. It's the same behavior that you'll see. So Phil has this in his paper with Hongyi. Like we found this for properads a long time ago when we were trying to construct a homotopy coherent nerve for operads. And so he wrote it out in that paper with Yi, like the explicit obstruction. It's probably a similar thing. I think it's quite similar to the notion of whether or not a polynomial monad is tame. I think Clemens is in, and I think the one for modular operads is not, if I'm correct on that one. So I don't actually expect there will be, not equivalence. You can still construct like a homotopy coherent nerve just by taking a W construction like you would in the operad case, but I don't think you're going to get like a model category equivalence there. Something a bit weaker.
Okay, thank you.
Thank you.
Yeah.
Is there any other question here or somewhere else in the world? If not, may I comment the very end of your last slide?
Yeah.
And I apologize in advance because I'm going to cite my own work. It is indeed
Okay,
It is indeed very interesting to prove that, as Ben did, that the groupoid colored opera which governs modular opera is causal. Because then you have good models to, you have good resolutions to describe the deformation complex of morphisms of modular operas. And for instance, one of this is the definition of a cohomological field theory, which is exactly an algebra over the chains of the compactified modular spaces of curves. And this is there where you have the Gromov-Witten invariance and some interesting stuff in integrable systems. And using this deformation complex, we showed that we have a big universal group of symmetries acting on that, which contains GRT, using the work of Wildvarer and Merkulov. And then also inside that, we're able to plug, for those of you who know what it says, the given tar group. So this is very useful that Ben proved that this groupoid colored opera disclosure.
yes.
If anyone is interested, I'm very happy to chat about that, of course.
Is this a good enough reference? Do you have like many papers with cohomological field theories in the title, or will this point people in the right?
And I should cite my co-authors, but I'm tired too. I did that with Vladimir Dotsenko, Sergei Sharin, and Arkady Weintraub. So the Weintraub family has been cited here. It's not Dimitri on the previous talk. It's Arkady here.
All right, I had a D and a V, and I missed the one in the middle. But we can put it in the chat in a bit.
If you have questions, send me an email, or here we can chat.
Yeah, very nice.
Sorry for the self-promotion.
No, that's good. And
another incarnation of Grothendieck-Teichmüller. That's maybe the interesting part of the story for you.
About the Grothendieck-Teichmüller. So I'll just a little preview for tomorrow. So there's from there's the Grothendieck-Teichmüller group here with Pedro and Geoffroy. But tomorrow I'll talk to you about related groups to the Grothendieck-Teichmüller. So one is a group that by Nakamura and Schneps called Lambda. It's a subgroup of GT hat. So it's a big profinite group. And it still contains the absolute Galois group of Q. And well, they don't know, nobody knows if this is a proper subgroup. Yes, thank you for putting the spelling in there. You can't throw a Russian name at me like at this time of, well, actually at any time of the day, to be honest, and like expect it to go well. So apologize for Vladimir. So there's this nice group here, and we sort of expect this to be automorphisms of some so right, I said that PARB, well, this is closely connected. And I'm being really fuzzy here with the moduli space of genus zero curves. And this will be closely connected. And again, this is a lie. So just closely connected to higher genus curves. We'll talk about, I don't have a proof of this yet, but I have something close to it. And we'll talk about that tomorrow. Sort of aside, since I'm already doing this, there's this whole other story. I intended to ask this at the end of next time, but this is like a question for the audience. So there's this whole other story of these Kashiwara-Byrne groups. So there's this, so we've been talking about associators in Daniel's talks. And so you know that, you have GRT, these are pro-unipotent groups, what I'm writing down here. So I'll put the Qs. Acting on the class of Drenfeld associators. And there's some higher dimensional version called the Kashiwara-Byrne equations. So these are solutions in a Freely algebra. And I know there exist maps here. So what's interesting is that these are related to modular operads as well. So in a paper that I just finished with the archive, I've been able to show that at least rationally, this is something which is automorphisms. This is something called W phones. It's like a non-connected modular operad. It has some free-floating loops that make it hideous, but it's basically a modular operad. Sorry, this is a Q. And I'm wondering what would be, if there's anything interesting to say about like what, right? There's no reason you can't just take the profinite completion of this thing. And so it's embarrassing to say this on recording, but I had a question for the audience was, does a profinite version of the group KV, so this Kashiwara-Byrne group, make sense? There's a paper where GT1 sits inside of KV. Well, profinite by Schnaps, they don't define any KV. Every element of GT1 satisfies the equations of KV. But does this make any sense? Which is kind of a weird question to ask a bunch of people, but this is an audience who might actually know if there's an idea of profinite Kashiwara-Byrne. So there's, and these are, as I said, automorphisms of a particular, it's a type of modular operad that comes from low dimensional topology, at least rationally. So I'm curious to know if it has any, if there are any extensions of it. So if anyone knows, please let me know.
I will leave them this exercise for tomorrow. Is there any
This is a very simple exercise for tomorrow.
Depends for who. Is there any other question? I have one comment. You should not have said Kashiwara-Byrne. So in the last paper of, I'm sorry, that's going to be my last, I think we are discussing with Marcy. Okay, look, in the paper of Alexeyev, Kawazumi, Kuno, Naev, where they study the formality of the Goldman-Turayev-Lie bialgebra. Alors, be careful, it's not formality in the sense that we saw here. They have an involutive Lie bialgebra, which is filtered. They pass to the graded guy, and they ask whether there is an isomorphism between the guy and the graded guy. So that's what they mean by formality. So don't be confused, it's not formality. Okay, so this is the problem. And Alexeyev, Kawazumi, Kuno, Naev show that it is related to Kashiwara-Byrne. Okay, you have to start from a surface with certain genus and boundary components. Okay, so genus G and N boundary components. And this is related, so the Goldman-Turayev problem for genus 0 and 3 boundary component is equivalent to the Kashiwara-Byrne problem. Wow. But okay, we have this for any genus and any boundary component. So they coined a Kashiwara-Byrne problem for any G and any N. But when I read their paper, you see they have species, they have many functors from sets with genus and G genus N boundary components. So exactly your functor where you labeled your graph with stable things. And I was wondering, they have all these constructions, species-like constructions, pi1 of the surface, or the Momili algebra of the surface, etc. And they come in collections labeled by this G and this N. And it seems to me that everywhere in their paper, there should be modular operad structures. So you see the pi1 should form a modular operad in groups. The Holonomili algebra should form a modular operads in Lie algebras, etc., etc. And why I'm saying that is because their proof of the higher genus Cauchy-Varaverne problem, they solve it in genus 0, 3 boundary component. They prove it for genus 1 and 1 boundary component, and they say, oh, and this is it. Why? Because I think the modular operad is generated by these two guys. So have you understood that? Could you explain that to me?
So actually that means that you answered my question, but not the other way around. So the version of this modular operad I have is actually constructed from something called well-defined. So this is I used a bijection of Barneton and Juji Dansho, which says that sort of solutions to KV. So this is the original, I guess, I don't know, genus 0, Cauchy-Varaverne, the original Alexiev and Teresian paper are in bijection with these things called homomorphic expansions of a type of knot that is knotted surfaces in R4. So it literally is higher dimensional. I have not yet understood the Goldman-Toraev point of view, but it is worth looking at.
Okay, this is an exercise. If anyone can, the last of IXLF Kawazumi Kuno Turayev paper, and can you tell me if my idea is not a conjecture, if these constructions actually form a modular operand in blah 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 category? My feeling is that it should help organizing what's going on here. So.
That would probably really help. That's a great idea, Bruno. So thank you. You answered my question, not the other way around.
That's the feeling you have. Okay, I will stop bothering everybody. Is there any other question? No. Alors, let's thank Marcy again.